speaker is Honghao Lin, and we will speak about the strong separation for adversarially robust and zero estimation for linear functions.
Okay, thanks for the introduction. In this talk, I will introduce our work about attacking on linear sketch for zero estimation. It's a joint work with Elena, David, Houghton, and Simpson. I think David, Elena, and Simpson are here. Okay, so let me first go through some background here. I think you should have seen this a number of times. So I will just do some quick recap to refresh your mind. Okay, so we will consider string models. We assume there's a universe from 1 to n, and there's a corresponding underlying frequency vector x, which initializes to be 0. Then we will see a number of strings, a1, a2 to an. Here, when we see the items at, means that the frequency of the item at will increase by 1. You can imagine that we insert at into our storage. Then at the end of strings, we want to either give a evaluation or some approximation for fx for a specific function f. And here our goal is we want to use the algorithm, use the space sublinear in the input size n and the string length m. Okay, so we can also consider the following generalization. So imagine that when we see the item at, we also see a update value wt, means that we change the frequency of the at by wt. And in general, there are two widely studied models in this setting. The first one is the insertion-only strings. It means that here the wt can only be positive. The second model is the insertion-deletion string. So it means that wt can be either positive or negative. Okay, so in this talk, we will focus on the distinct element problem, also called L0 estimation problem. Here, L0 will be the value of the non-zero coordinates of the frequency vector x. And here our goal is like given an accuracy parameter epsilon, one algorithm output one pass epsilon approximation to the value of the L0. The distinct element has a number of the real-world applications. For example, imagine in the internet traffic monitoring programs, the item we see can be seen as a number of the IP addresses. Okay, so in this workshop, we will focus on the adversarially robust string settings. So in these settings, we assume that the update to the vector s can be arrived sequentially and adversarially. So we are imagining that adversary want to use a number of queries to learn the internal randomness of our algorithms. And it want to generate some input to break these algorithms. Here, the key feature is the future queries may depend on the previous queries. Imagine that a typical scenario is that in a database system, some user may consistently make some queries and want to break these databases. Okay, so for this purpose, in the initial-only streams, the first work was in 2020. The Benzes et al. Proposed the sketching switching methods, which achieves adversarially robust string algorithms in the space 1 over epsilon cube times polygon. Later, it was improved to 1 over epsilon 2.5 times polygon via the differential pair with tools. And finally, by the difference estimator, it was improved to 1 over epsilon squared times polygon. So that means that for insertion-only strings, we can achieve nearly tight results for adversarially robustness. However, for the insertion-deletion strings, the thing becomes quite different. So a linear sketch is the useful tool to handle the insertion-deletion strings. So at high levels, the algorithm will maintain AX for some specific design matrix A throughout the strings. And in the string models, because we are caring about the bit complexity, so the entries of the matrix A should be polygon bounded. The advantage of the linear sketch is easier to maintain the memory. As we can see, if the delta t is the vector of the input, we can then just update the sketch by a delta t. Then after the strings, the algorithm will output the GAX for some specific post-processing function G. Okay, so as introduced by David, so in 2013, And would you suggest that the following attack? I would suggest that a linear sketch with R rows can be attacked by poly-R parties. However, there are two main limitations about this work. The first one is this attack only works on real value inputs, and it has been addressed by the talks by David and Elena. The second issue is this attack only works for LP estimations when P is larger than 0, and such attack doesn't work for the case for L0 estimation problems. So in this talk, we will focus on the second problems. Okay, so what we show is the following. So assume A is a linear sketch, which you can produce a 1 + epsilon approximation to the L0 value on adversarial inversion division string for some constant epsilon. And this sketch matrix A uses R rows here. R is smaller than n to the 1/4. And each entry of the matrix A is polynomial unbounded. Then this sketch can be broken in until R to the 8th parts. Okay, before we move to the intuition of the attack, any question here?
Is R to the 8th type or?
It's an open question. I will discuss here. Okay, so next I will give some intuition about our attack. Okay, so instead consider the general L0 estimation problems. Here we consider the so-called gap L0 norm problems. So let alpha and beta be two fixed constants. Here our goal for algorithm is to distinguish between the L0 norm of X is smaller than alpha n or larger than beta n. And if neither of the case holds, the algorithm are allowed to arbitrarily output. We can see that for some small alphas, any algorithm solve the L0 estimation problem can solve this gap L0 norm problems. Hence, if we can design attack against the algorithm on these problems, we will immediately get the attack on the algorithm for L0 estimation problems. And let us first consider the following motivation questions. So recall that the linear sketch first compress the original vector x to a sketch vector ax. Here the ax is a r-dimensional vector, so it means that it may only contains roughly r log n bits of information. Hence, there should be only a small fraction of the coordinates can be learned well by the sketch matrix A, but most of the coordinates are not. Here we call such coordinates are significant coordinates, and the remaining coordinates are non-significant coordinates. So what does the significant mean here? Let us consider the following examples. So here is the sketch matrix A. You can see that the first law of the sketch matrix is a one-sparse vector. Hence, by look at the inner product of the AX, by look at the first coordinate of the inner product of the AX, we can know the first coordinate of the X immediately. So it means that the first coordinate should be the significant coordinates of this sketch matrix. Any question? Okay, so it's just a simple example here. I will give a more detailed discussion in a little. Okay, so at high levels, the strategy of our attack is as follows. So our adversary wants to gradually learn the sketch matrix. So it will iteratively identify the significant coordinates and set them to 0 in all future parts. Then after we have learned all such coordinates, the query algorithm, we can mark these such significant coordinates to 0 in our future parts. Then the query algorithm can only rely on other coordinates for which the sketch matrix, the sketch AX only has some small amount of information. We can first consider these extreme examples. So consider the sketch algorithm is quite simple. Like it's just the sample subset S of R coordinates of the original vector X, and return the estimation by the scale. Then the procedure of our attack will be, we will try to identify such subset S, and we will put 0 in S and non-zeros everywhere, so the algorithm do not have any information.
So it's basic idea like in the F2 attack to find the vector in the kernel.
The sense is exactly, yeah. But the definition of significant coordinates is somewhat different. I will discuss later. But the question is, how can we identify such subset S? We first consider these simple examples. This motivated us consider the following interactive fingerprint code problems. We consider the following form we are interested. So imagine they are an attacker and an aggressor. The aggressor holds a subset S from the universe 1 to the n. And the goals of the attacker is it wants to make a number of adaptive queries to learn this subset S. The rules are as follows. So at the time t, the adversary can query the binary vector, n-dimensional binary vector qt. And the algorithm will observe the qt on each subset S, and will need to output a response AT. Here, the rule is if the qt on S is a O1 vector, the AT must be 1. And if the qt on S is a 0 or 0 vector, then AT must be 0. And if neither of the case holds, the algorithm can allow arbitrary inputs. And this fingerprint code problems has a number of real-world applications, such as the watermarking or treasure trace strings. And in the work of the string and the woman in 2015, it also shows that there is this interacting fingerprint code problem with roughly altered S-square queries. Here we give very high-level ideas about their attack. So at high levels, their algorithms maintain a score Si for each coordinate I. Then at each round, the query will first sample probability P based on some specific design distribution. Then the query Qt will be n-dimensional Bernoulli vectors. Then after seeing the response from the algorithms, the attacker will update the score Si based on this response. And intuitively, if the response is the same as this coordinate, it will increase the score. And if the response is different than its coordinate, it will decrease the score. And if for some I, the Si is larger than some threshold, the algorithm will climb. Okay, so this coordinate will be in this subset S. And it will repeat this procedure iteratively. Okay, so let us make a comparison between the fingerprint total problems and our gap at zero node solution problems here. So for the fingerprint code problems, the algorithm just need to respond truthfully when the queries on S is or 0 or 1. But for our gap at zero node problems, it need to distinguish the two cases, the zero node of X is smaller than alpha n or larger than beta. So it means that these problems, the attacker can get more information from its queries. So follows a similar analysis of the fingerprint code, which will get the similar kind of attack still goes through. But the issue here is the sketch X for the fingerprint code problems. There's the assumption that the algorithm here can only observe the query vector on its subset S, but it cannot observe the Q outside its subset S. But for our case, the sketch matrix A may also consider some part of the information about the other insignificant coordinates. Okay, so there are two questions need to be solved. The first one is how to formally define a condition for significant coordinates. Hence, other this definition, we can identify and avoid them. The second case, the second problem is how to get around with the remaining coordinates. Okay, so we will first consider the first problems. Okay, as we have seen the examples, basis vector EI. If for some rows of the matrix A is a basis vector EI, then this I should be seen as a significant coordinate. Let us consider the next examples. So in the scaling matrix, we have a 99 here. So by looking at the second entry of the AX, we can get the value of the second coordinate of X immediately. So it means that the second entry should also be a significant coordinate of the schedule matrix A. Similarly, if we can have if there exists ij such as the square value of the aij is larger than 1OS times the square 2 norm of the row ai, then j should be a significant coordinate. But let us consider these examples. So for these two examples, both A1 and A2 are non-sparse, but the A1 plus A2 is one sparse vector. So it means that by reading the value of the inner product of the A1 plus A2 and with X, we can get the value of the X4 immediately. So it means that the fourth coordinate should be a significant coordinate of the schedule matrix A. So we can generalize the ideas as follows. So since we are allowed an arbitrary post-processing to our schedule matrix A, so suppose there exists a sequence of the low operation, such as after this low operation, the ith coordinate is takes up at least a 1OS fraction of the whole rows. Then I must be significant coordinates. And if you are familiar with the numerical linear algebra, here the definition of this corresponds to the Lagrange score of the coordinate. Okay, so now we have the two conditions. The question is whether these two conditions is enough or not. Let us consider the next examples. So in these examples, the 3 is the smallest entry, but by looking at the inner product of the A1 and X, we can also know the value of the last coordinate of the vector X, because this reveals some information about the X modulo 10. And we can also see this schedule matrix as the list form. So this suggests that the fractional part of the schedule matrix also need to be considered. So we can next consider these conditions. So suppose there exists a sequence of the low updates, low operations, such as after these low operations, the fractional part of the sum coordinates takes up at least 1OS fraction of the fractional part of the whole rows. Then we will treat this I as a significant coordinates. Okay, so now we have all the 3 conditions. And if we look at it carefully, the condition 3 actually implies condition 2 and condition 1. And it turns out all the condition we need is the condition 3 here. Before we move on, any question here? Okay. So next we will show that after we have the significant conditions, we can actually next pre-processing the schedule matrix A. It's just a source experiment to help us understand better. So consider the actual schedule matrix is the following, and it has a 999 at the second rows. Then we can without loss of the generalities to be 0 these columns, and we make an extra columns and make which is a one sparse vector with a 1 here. Then the key observation is without loss of the generality, we can assume the algorithm actually use A prime instead of the matrix A. The reason is since we are allowed an arbitrary post-processing algorithm, so if the algorithm look at the A prime, it can just add this row back to the previous rows and can recover the schedule AX. So it means this step only gives the algorithm more information. So similarly, we can do this procedure iteratively. So whenever there's a significant coordinate I, we can 0 these columns and add a row EI. So it will result in a matrix A prime, which can be seen as a combination of the sparse part S and the dense part D. Moreover, we have the row of the S is one sparse vector, as when we add these rows is a one sparse row. Then the dense part D will have no significant columns. Moreover, the columns of the S and D are disjoint. Okay, so one immediate question here is how many rows we will add in this procedure? Because we don't want to add too many rows to the schedule matrix A, And fortunately, we show that in this procedure, we will only add at most RS login rows. I won't go through too many details here. The thing is, we prove it while information theoretical argument. So suppose we add M rows, we can argue that for some specific distribution X, the AX will reveals at least M over S piece of information. And since each coordinate of the sketch matrix A is Polian bounded integers, so each coordinate of the AX will contain at most log 1 piece of information. So combining this part, we will add at most the RS log 1 rows. And recall that if we can show that from the dense part, we cannot get any information, then we can use the fingerprinting code to learn the location of the occurrence in S. So we can put a 0 in our future query, so which will make the algorithm fail. Okay, so let's turn to the second part about how to get along with the remaining coordinates. I will just give some high-level ideas here. What we do is we design a family distribution D over the integer support from -R to R. Here R is bounded by poly RS times log n. And what is the property of such distribution family? So for each value P in this range AB, the DP in this family will be a distribution such that if X is sampled from DP, we have the probability X be non-zero is exactly P. The second thing is for any value P prime in this range, the total violation distance between the DXP and the DXP prime is small, up to 1 over polylogan. Here D is the dense part, which has the condition that has no significant coordinates. And here the XP can be seen as the n-dimensional vector, where each coordinate is sampled from DP. Okay, let us consider why this distribution is helpful. First thing is imagine that if X is sampled from DP to the N, then the expectation of the zero norm of the X will be exactly P times N. So it means that for different value P and P prime, the X and X prime will correspond to different answers of the gap zero norm problems. Okay, the second thing is let us look back to our sparse density compensations. In these compensations, AX can be seen as SD times X, which since the non-zero columns of the SD are disjoint, so it can be seen as the N times X combined with the D times XD. And from our total violation distance conditions, we have the DXD doesn't reveal the value of the P here. So the only informative part is the S times XX. Okay, so let me make a summary here. So the first step is we pre-process the sketch matrix A into a sketch matrix A prime, which can be seen as a combination of the sparse part S and the dense part D. And it's just a third experiment, means we don't actually need to pre-process the sketch matrix A, because our attack agent doesn't know the sketch matrix. But it's the thing is we show that attack matrix A is equivalent to attack the matrix A prime. Then we want to use the fingerprinting code to attack the sparse part S. Means we want to learn the location of the zeros of the sparse part S. And to make it this attack help, we need to design some distribution which makes the dense part doesn't help on the fingerprinting code queries. Okay, so the final question is how to construct these hard distributions. I won't go through too many details here due to the time constraint. At very high levels, we use the Fourier analysis here. And it turns out that after we have the conditions D doesn't have any significant columns, the only condition we need is the moment matching conditions. We need for the first for the X from DP and the DQ, we need to their first K moments are matched up to K equals to order of the R log n. And to achieve these conditions, we consider use the specific polynomials in the work of the Larsen-Weisstein and in 2020. Okay, so let me put everything together here. So the first step is we do a thought experiment, pre-process the sketch matrix A into a sketch matrix A prime with at most RS log n rows. Then we design a family of the distribution D, which makes the dense part not helpful. And to get this desired bounds, we need to set the S correspond to the significant conditions the order of the R cube times polylog. And note that here, the location of the sparse paths correspond to the set S in the fingerprint code province. So it will has roughly RS log n rows. So it will at most R to the fourth polylog n rows. Since in the fingerprint code, we need to S square number of queries. So our total number of queries will be R to the S. Okay, so let me make some summary here. So in this result, in this paper, we show that any integer-based linear sketch for adversarial estimation can be use roughly R to the S queries. We also give the additional results about if the sketch matrix A is on a finite field FP or on the tag is on based on the real value tag. I think both of the bounds has improved by the talk yesterday. So one remaining open question here is close this gap to about the integer case. Currently the up bound I think is still R to the S and the lower bound is R squared. Okay, so any question?
I have one kind of high level, which is like at what point did you use that we were using the problem was about distinct elements? Like you're using very general techniques, but like at the core, like where do you really need the fact that it's distinct elements?
So here the fingerprint code program assumes if the O1 is mass out 1, if this O1 is mass output 1, it was O0 is mass output 0. And here in our case is if the L0 or is smaller than alpha n is so I think it's the one place we need about L0 nodes. It's a second place is okay.
So we can also take this offline.
Okay. So when we for fingerprint code, the query is a binary vector. In our case, the query is a number binary vector, but we need to treat it as a when we update this score, we need to treat it as the binary ratio of the input vector. So I think the LP norm doesn't apply.
I see.
This another intuition is like the L0 sketch, the non-robust case is sparse actually.
I see.
But for LP, actually there are fine dense sketches that so even in a non-robust case, it's even.
So you can do like sparse recovery because it's a sparse.
It's somehow important that the non-robust sketches here are sparse.
Okay.
It seems in your talk you need to set query vectors with negative entries.
Yes.
And can you make it not happen? Because I mean, if you're monitoring a network, there are not going to be IP address attributes negative and adding.
So I think if the coordinates cannot increase, we have the upper bounds. So
Alright, but I mean,
you are saying that we can increase the coordinates.
but subject to the condition, it cannot go below 0.
Yeah, I think it's another open question. It's about the algorithm or lower bound for we call the strict tensile string models. I think. So
it's open.
Yeah, it's another open question. So means that we can decrease the entry, but the entry cannot be go down 0.